I've been at Lawrence Livermore for 25 years. I came as a graduate student in the laser program, so if I had to self-identify technically, I would be a high energy density scientist. When I started in that field, it didn't exist, so I was a strong field atomic physicist. Worked with Ray and his colleagues and folks at Livermore for many years doing laser experiments. So if I had to have a real job again, that's what I would do. I'm currently a manager. I manage, as Ray described, the nuclear counterterrorism program at Lawrence Livermore, which is about as distant from where I started as I could imagine. And program, N is an overused letter at Livermore, N is for nuclear. So now I have very deep ties to the nuclear science community at Livermore, including the nuclear and radiochemistry folks who do nuclear forensics, and the nuclear physicists who support our device assessment activities. And in my prior role, I managed the materials research portfolio. So, I'm a great friend of the disciplines that are represented here. And I've been a party to the SSGF from the very beginning. So I spent 2 years in Washington working in defense programs when this program was first stood up. So this is one of my favorite gigs, as I tell John every year. Don't throw me off your committees, because I really enjoy it. So thank you very much for letting me come again, and it's wonderful to see so many first-rate students. I'm pretty confident I wouldn't have been in your ranks when I was a student, but now I'm here. I'm going to tell you a little bit about Livermore, and it's going to be a pretty high-level flyover so that you get a feeling for what the labs are like. Most people don't have a clear idea of what the national labs really look like until you go there. I certainly had no idea when I showed up at Livermore. A little bit about our mission space, which is very broad. I firmly believe our core mission is nuclear security. We're a national security lab with a nuclear core. We support many sponsors in my program. I get $5 from everybody in the government. So I work for Homeland Security, the intelligence community, the Justice Department, the DOD, and NNSA. Our core really is the idea of doing multidisciplinary science and engineering. And I'll show you a chart in a minute that tries to express a little bit how multidisciplinary that is. And a key for us in this is that we are able to form teams around important problems that face the nation really dynamically. So the teams change all the time. And if you need a computer scientist and a materials scientist and a high energy density scientist and an engineer, we can make that happen on any given day of the week. So it's hard to imagine a topic you could bring up that there's not someone within the square mile that is working on it, which makes it really fun. And again, it allows for this broad experience that I've had. And we're really proud of the fact that we turn ideas into solutions for the nation. So the people who work for me do things like support emergency response. So if there's a nuclear incident, I have people who actually go deploy into the field and support law enforcement or the Department of Defense in responding to some kind of nuclear issue. And people who build hardware that goes into the hands of operators out in the field. So very exciting, very tangible, very strong sense of satisfaction from supporting that kind of work. But not possible without this really strong foundation of basic ST&E. And I'm equally passionate about that component of what we do. I like my folks to be involved in the science community, and I encourage them to publish and to go to conferences to the extent that they can, because it's really important for us to stay at the leading edge of what we do. So Livermore is a small laboratory. Our main site is 1.2 square miles. This is the Livermore main site. We have a large experimental test site through the hills in Tracy, California, that we also use where we do things like explosive testing and increasingly new mission spaces like energy research. For example, proposals to put solar energy and windmills out at Site 300 to make it a test bed for renewable energy research. We have about 6,000 career employees with a budget of $1.6 billion. We used to be substantially larger. This is sort of our post-contract transition stable equilibrium. And about a third of those are scientists and engineers. I have to show an obligatory org chart. I've worked in all the major program directorates at the laboratory and the Physical and Life Sciences Directorate. So I do have, as Ray said, a broad view. Anyone who wants to know more about any of these topics, I'm happy to talk. And I have my business card if you'd like to get in touch later. Our new director is Parney Albright. Parney's unique in the history of Livermore. He came to us from a career mostly in government. Homeland Security, he helped stand up S&T at Homeland Security, and we hold that against him to this day. So he's really trying to give us this, open our aperture. We have this nuclear core, and these missions are very important, but the things that we do and have developed as a part of that core mission really can broadly benefit the nation. So we're spending a lot of time thinking about that mission space. Lots of scientists and engineers, strongly peaked toward PhDs, but we have a lot of master's and bachelor scientists as well, particularly large populations of engineers and computer scientists who have, my husband's a computer scientist. When I got my PhD, I got a postdoc. When he got his master's in CS, he got a staff position. And a wide variety of technical disciplines. You see, dominated by engineers. We are known for building big, one-of-a-kind, first-of-a-kind experimental science facilities and tools. So the National Ignition Facility is a classic Livermore accomplishment. Second peak is physicists. The standard statement on the laboratory is it was built of the physicists, by the physicists, for the physicists. It's changing over time. Material science in particular is becoming a very strong component of our technical workforce. We're right next to Silicon Valley, so computer scientists are a very, very dynamic population for us. And then a long trailing list of, other is a pretty important category here. As I said, we have a huge number of disciplines represented under these broad categories. And we do lots of different things. So our core mission grows out of our activities in support of nuclear security and the Stockpile Program. The preponderance of the laboratory supports the Nuclear Weapons Stockpile Stewardship Program in one way or another. And that's probably 3/4 of our activities at the laboratory and our staff. And a wide range of our science programs are really most strongly supported by that venue. So the budget in the core weapons program for fundamental ST&E is very substantial. And that's both experimental research and computational research, very strong in both. I work in this arena now, international and domestic security. We do work in support of the Homeland Security Department, aviation security, explosives, chem and bio defense, very strong programs, particularly in bio, where we, again, operate reach-back capabilities in the event of bio events. And a growing focus on energy and environmental security. Livermore has a long history in climate science. We're the home to the PCMDI, the Program for Climate Model DI. I blew it. Anyway, this is the team that takes all the climate models from around the world and compares them against each other. They've contributed strongly to the IPCC reports on climate change, and we're party to the Nobel Prize that was awarded in that area. So very long and distinguished history in that arena. In energy, our programs have tended to oscillate over time, depending upon what the nation is interested in. Energy has never really become a stable focus for the government, so our programs reflect that, although we have growing activities in renewable energy, and in particular, because of our expertise in geoscience, which is, again, built on the foundations of having studied nuclear testing, both our own nuclear testing and test diagnostics for folks around the world. We're very good at studying things like fracking and non-traditional oil and gas recovery, things like that. And it's built on a foundation of capabilities. So basic science, we have strong programs in the core disciplines, as I said. Huge investment in computing, and Livermore's been at the fore of the ASC program from its beginning. We currently host the world's #1 machine, Sequoia, and engineering. So this is a picture into the NIF laser bay, and if you ever get a chance to go to Livermore, it's impossible to go to this facility and not be impressed. Even if you're not interested in high energy density science, it's quite amazing. And broad scientific and technical capabilities. So, again, core activities surrounding disciplines that you don't learn in school. So we don't hire people out of nuclear weapons science and engineering departments. Very strong expertise in diagnostics and sensors. I'm an experimental scientist, or a blue-collar physicist. I built things and did experiments and worked hands-on. Livermore was very good at that, and my philosophy was always have skills, will travel. I knew how to do things and build things, And I could do that for high energy density science, or I could do it for materials, or I could do it for nuclear science. You can learn the physics, but the skills are very important foundationally. And again, systems engineering, one-of-a-kind, first-of-a-kind systems, high-performance computing, strong programs in intelligence and network analysis. We have a large program that's actually has its roots in the 1960s in intelligence, support to the intelligence community. Earth and atmospheric science, again, in addition to the PCMDI activity, which I still don't remember what DI stands for, we're the host to NARAC, the National Atmospheric Release Advisory Center. So if there's a release of any kind, it was originally founded to look at nuclear releases. So see 3 Mile Island, you want to know where the plume is going, how to evacuate people. But they can apply that capability to a broad variety of releases to help. For example, in the response to the Fukushima disaster, NARAC worked 24/7 providing plume diagrams to help guide the evacuation of folks in Japan. Chemistry and materials, a picture into our high explosives area. We have very extensive capabilities for blowing things up. That's another core competency and a lot of fun. And then laser science and technology. And I told you that it was of the physicists, by the physicists, for the physicists, but LLNL is widely rumored to be lasers, lasers, nothing but lasers. So one of our key science highlights, and just sort of proof of concept, we really do fundamental science. If you've been watching the news on the two new elements added to the periodic table, Livermorium and flerovium were discovered by a joint team, Russians and Livermore scientists. This group has added a number of elements to the periodic table. We just got the official word a few months ago that Livermorium would be the officially adopted name in the community, so we're very proud of that. And we have a category of investment internally that's discretionary to the laboratory-directed research and development. And that type of funding is very important because it allows us to do things that are well outside the mission space, but that ensure that the very best scientists stay captive and stay excited and stay interested in their work. And then we capture them into the missions. So the folks who did this work also support my nuclear forensics program as their day job. But this is a very important component of what keeps the laboratory exciting and what keeps us moving. So here's the team. This is Don Shaughnessy. Don is one of the lead scientists, as I said, in our nuclear forensics program, and also is one of the pioneers in using NIF and our high energy density platforms to do nuclear forensics research and radiochemistry. We're very proud. We have one of the few, what I would call live fire radiochemistry facilities in the world. Very important core competency to us from our weapons testing days. That was a key diagnostic for understanding underground nuclear tests. It's now a key diagnostic for nuclear forensics, where we try to tell from the debris, if there were a nuclear explosion, what type of device was detonated and use that to support attribution processes. And Ken Moody, one of our key senior scientists in this area, who's a long history and is one of our new distinguished members of technical staff. These teams, as I said, move very fluidly amongst the programs, and to most people's surprise, our group in nuclear and radiochemistry is actually quite young. So Livermore has very strong programs in fellowships and training with Homeland Security and with NNSA in an effort to maintain that key nuclear discipline for us, which not too long ago was in danger of disappearing. So very strong ties into that community. We have a lot of big facilities. The national labs typically host some number of large-scale facilities because it's something that we're uniquely well suited to do. In our case, we have some really big facilities. So you've heard, I'm sure, of the National Ignition Facility, world's largest, certainly by scale and by energy. Laser recently achieved their 2 megajoule performance target, so just an amazing engineering and laser science accomplishment. 192 beams, and primary mission, again, is trying to achieve ignition in the laboratory, but it's one of the key Stockpile Stewardship Science platforms that we use, because you can achieve truly unprecedented energy densities in that forum and do amazing science with that. High performance computing, as I said, Sequoia, we're number 1. Very excited about that, and we have a long history in computing and in pushing both hardware and software paradigms. And then this is our unique high explosives application facility. We have the ability to do experiments up to 1 kilogram of explosives in a containment chamber in the basement of this facility. So really exquisite diagnostic capabilities for what are, if you're a chemist, that's really complicated experimental science. And then different facilities. The Center for Accelerator Mass Spectrometry is a place where we do very detailed analyses of very minute quantities of materials. So one of the things that was done at this facility was they were able to make environmental measurements and differentiate between, support the science behind the climate change scientists, again, showing the human impact on carbon in the atmosphere versus the naturally occurring carbon cycle in the atmosphere. And our Forensic Science Center is another unique activity. This group supports law enforcement and can do very detailed technical analyses of a wide range of samples, everything from contaminated evidence contaminated with explosives or radioactive material, through to being one of the organization for the prevention of chemical weapons certified laboratories. Only 2 laboratories in the nation are certified to do that work, and the Forensic Science Center is one of them. And as I said, I have folks in my organization who do operational activities. The laboratory has a wide range of 24/7 operational capabilities. I mentioned NARAC earlier. CAPS is the Counterproliferation Analysis and Planning System. It's a tool for the warfighter. It has very detailed databases of facilities and assets around the world so that as troops go into areas they're unfamiliar with, they can do detailed planning about what they might encounter. So if you're going to drop a bomb on a facility, you probably want to know that you're not going to blow, a bioweapons development facility or some store of hazardous chemicals sky high. The Biodefense Knowledge Center, again, a reach-back capability for biodefense. We have very expert scientists who really understand the biothreat and can provide support in that arena. And then, as I said, the Forensic Science Center. And the Stewardship Program, at our core, has been unbelievably successful. And I think all 3 laboratories share in this success. We have maintained the safety and security of the U.S. nuclear weapons stockpile since 1992 without underground nuclear testing. We've shifted from a test-based program to a computationally based program. We've built amazing experimental capabilities to replace the capabilities and experimental environments we had during the days of nuclear testing. So really quite an amazing accomplishment. And, able to do things like provide components and replace defective or aging parts if there are material scientists in the room, trying to understand how materials will be compatible with each other over decades is a very hard problem if you don't have decades to figure it out. So amazing strides in some of the fundamental science to pursue this very applied mission. And a number of successes in this arena that we can't talk about, but trust me, they're amazing, whereby we saved the country billions of dollars by applying science as opposed to building facilities or rebuilding things. So very amazing. And this is the key to where our tools come from. So, Stewardship Science is the engine that really drives all the scientific programs at the laboratory. The National Ignition Facility is built up out of the needs of the nuclear weapons program to have a high energy density platform as well as a burning plasma platform to investigate the kind of science relevant to nuclear weapons. Our computing capabilities, very strongly driven in this arena, although we have a very large unclassified computing capability to go along with it. And this is the advanced radiography capability, which is at Los Alamos. The nuclear weapons laboratories are a system. Each of the labs has very unique capabilities. We work very closely together. We compete in some areas where it really matters. If it's high consequence, high difficulty questions, we tend to compete. In the area of experimental science, we tend to collaborate very strongly because you only need one National Ignition Facility, one Z facility, one DART facility. So National Ignition Facility is our flagship with these 3 mission spaces. The vision has always been that fusion energy is the future. I'll resist the cynical comment that usually, 20 years from whatever day you ask. But the key missing piece, we understand fusion energy works, the key missing piece is demonstrating that in a laboratory setting you can actually achieve ignition. In the limit of enough drive and a robust enough system, we know that we can make fusion work. That's not an issue, but the complexity of the physics in putting that whole thing together is really turning out to be an amazing challenge. This is a platform where you can study astrophysical conditions because we are able to create energy densities that are only achieved in the far reaches of the universe, at the center of our target chamber here. And as I said, it's a pillar of our national security programs as well. I just wanted to put one amazing accomplishment up from NIF. One of the key experimental campaigns from the beginning has been to try to push materials research into unprecedented regimes. It's very hard to get to very high pressures. Standard techniques, diamond anvil cells, get you to a few megabars in a static environment. Traditional small-scale gas guns will get you to maybe 10 megabars, depending upon your system and how you work things. But if you want to really do isentropic compression, so non-shock-driven compression, and you want to go to high pressures, the lasers and the pulse power machines are the only venues we've found where that's really possible. And the team at NIF, using a whole room to generate an X-ray bath, this very tailored X-ray drive then launches a very specifically shaped pulse into this step target. Measurements are made on the rear surface here with a VISAR system, a velocity interferometer, to map out the isentropic compression path that carbon goes through, and have made measurements up to nearly 50 megabars. So really impressive scale up. The time scales are short in these experiments. Laser pulses are tens of nanoseconds. With pulse power, you can go out to microsecond scales, but still really an amazing accomplishment. Modeling and simulation are a very big deal for us. As I said, by training and temperament, I'm an experimental scientist. I spent a few years doing simulations. It's a lot of fun. You can do many more things in a computer than you can do in the lab. Not always right, but it's interesting. And it really underpins everything that we do. So it's very unusual to have a program where we don't have both experimental and computational science components. They tend to work very closely coupled, and we tend to model our experiments very extensively. Now, it's true that the codes are exactly as smart as we are. So to the extent that we don't know things, the experiments tell us things all the time. As I'm sure Ray will attest to, the high energy density community in particular has taught the codes many things. But it is part of the glue that holds the whole system together. And I'll talk a little bit about my area. As I said, I'm about as far from where I started as I could imagine. I've worked in and around the national security community, mostly in the Stockpile Stewardship Program, my whole career. A year and a half ago, when I came back from my last gig in Washington, I moved into this counterterrorism realm. This work is very interesting and shockingly different, to my mind, from this core stewardship mission. So it's still about nuclear weapons, not about our nuclear weapons, about improvised nuclear devices. Strong linkages between counterterrorism and non-proliferation. The goal, as you go forward, those two programs share many, many common attributes. And the big reason that we're doing this is that the world has changed a lot. There was a long time ago, we were worried about the Russians. The Russians had a lot of warheads, we had a lot of warheads. The programs were very focused on building up U.S. capabilities. Broad variety of designs were put into our stockpile, and massive stockpiles were built around the world. Proliferation moved around the world, and not as many as were feared, but a number of smaller players entered the game. But today, we're very worried about a different threat. So it's not a question of massive exchanges of nuclear weapons across the pole, although that's always a possibility. I'm worried about nuclear weapons, nuclear devices, nuclear material in the hands of non-state actors. So our programs and our focus has shifted over time to accommodate that. It's really a different problem. I know what our stockpile looks like. I know what materials are in it. I know what conditions are achieved. And I can devote my scientific resources in a very focused manner to trying to improve our capabilities in that arena. When I start thinking about this one, the design space is wide open, the possibilities are myriad. And it takes a lot more effort to bring focus to something like that. In a shocking turn of events in 2010, the Department of Defense actually put preventing nuclear proliferation and countering nuclear terrorism at the top of their agenda. So even in the defense realm, the centrality of this problem has been recognized. And the problem is that it's not a single point problem. So if you look at, I mentioned I get money from everybody in the government. Here's an abbreviated list of the places that my program gets funding for, and the range of activities that we are called upon to support across this space. So the goal in the nuclear defense is to stay as far to the left of bang as possible. Ideally, you'd like to not have threat devices in any nefarious hands, and you'd like to be certain that capabilities are not built up that could turn into threats later in time. So we support the full range of activities, intelligence programs, non-proliferation, counter-proliferation, counterterrorism, crisis response and attribution, forensics, again, which spans this space pretty broadly, arms control, which is an emerging focus for this administration, and then consequence management. These capabilities support a broad variety of applications. As I said, the consequence management and forensics community and crisis response community actually supported the response to Fukushima because we know about nuclear things. So if you want someone to tell you what's happening in the core of a nuclear reactor or what the signatures look like that people were measuring, that's the community that you go to. So what's the problem? So if you distill it to its simplest instantiation, if your adversary goal is a nuclear weapon, you need 4 things, roughly speaking, assuming you're going to steal, make, or buy some sort of threat device. You need design information, and depending upon your goal, it doesn't have to be very sophisticated design information. I'm not thinking about ICBMs, right? I'm thinking about terror. You need manufacturing capabilities. Again, if you're not thinking about precision-guided munitions, this may not be as complicated as it sounds. And you need a delivery system. And when I asked the folks at Livermore to put together a view graph for me, they put an intercontinental ballistic missile in that corner. I'm not worried about that. I am worried about a Ryder truck or a rowboat or some other non-traditional delivery mechanism. So what's the problem? Nuclear material is where it's at. So if you can keep nuclear material out of the hands of the adversary, you can thwart this cycle. So most of the effort in the government has gone into securing nuclear material stocks around the world and ensuring that safeguards are put in place and that material protection, control, and accountability standards are achieved around the world, particularly in the former Soviet Union, but that's expanded really broadly. And also in gathering up orphan nuclear sources or bits of nuclear material around the world. So we've organized our program around the threats, this nuclear material problem. I'm not responsible for safeguarding it. I'm responsible for what happens if it gets in the wrong hands. So we have 3 focuses in my program. First is predictive process-aware material models. If I pick up a piece of uranium somewhere in the world, I want to be able to tell with high certainty where it came from, whose hands it went through, what kind of facilities it was in, how was it processed, and how could it be used. So much like the stewardship program, we're very focused on understanding material properties at a very fundamental level and developing ways to understand fingerprints throughout its life cycle. And for me, the life cycle is very broad, so I'm interested from the time it's dug up out of the ground all the way through to a post-detonation nuclear environment. We're interested in global situational awareness for nuclear materials. If I could tell you with certainty where every atom of every fissile material was at any moment in time, that would be great. It's a very hard problem. So are there ways that we can detect or diagnose the presence or the production of nuclear materials that can help in that goal? I don't think you can secure all the nuclear material around the world with high confidence. It's just, as I said, it's not just weapons-grade uranium and plutonium. If you're worried about radiological dispersal devices or low-yield nuclear weapons, your phase space is a little bit bigger. So we need a better way to think about understanding where the material is and most particularly understanding when it's moving in a way that we don't want or is not desirable. And then we need forensic capability. And for us, nuclear forensics spans this fingerprint notion for nuclear materials before they get used, all the way through to understanding post-detonation device debris and using that to determine what kind of device was detonated and who might have done it, support the intelligence community. So we want to change the game in nuclear security by pursuing transformational R&D on nuclear material properties, detection, and use. So very strong coupling into both the materials and nuclear science communities here. And a growing effort in high energy density science for this forensic application. And we use all the same tools. So my folks use NIF. Computing is still at the center of what we do. We do a lot of fundamental experiments. We participate in the academic community, so even in these really hardcore nuclear security mission spaces, we're still scientists and we still expect our people to be participating. And we do big experiments. This is people out at the test site getting ready to blow something up. Just, there are fun parts of this job too. So here's an example of a fundamental research project. Again, this is supported by LDRD at Livermore. The PI here is Ian Hutchin. There's a book you can get called Nuclear Forensics, which is the textbook on nuclear forensics. It was written by 3 folks at Livermore, Ian Hutchin, Pat Grant, and Ken Moody, who I showed his picture earlier. And Ian's LDRD project is focused on developing the scientific underpinnings for the forensics mission. They're looking at fallout, so they went out to the test site and gathered up debris from old tests, and atmospheric tests at the test site are from a very long time ago. We haven't done that in many, many decades. And they're starting to develop a different kind of understanding of what the characteristics of fallout are and how fallout is formed and what you can understand from the characteristics of fallout particles. Work done in collaboration with University of Nevada, Las Vegas. Some work in understanding uranium volatility. It's very tricky when you pick up, think about material going through a nuclear fireball and then falling out to the ground. It's very tricky to understand with high fidelity what you've got at the end of that process. So really trying to pull information out of that, and this is work being done in collaboration with the University of Bristol. And then this work up here is very interesting. So one of the problems for nuclear forensics is that radiochemistry is very accurate, but it takes a very long time. So you can imagine if there were a nuclear event, decision makers would be on the phone that afternoon. We want to know what it was, who did it, and what should we do about it. And if you think about the timescales, you first have to go there, then you have to collect debris, then you have to transport it to a lab to do separations, you have to count it. It can take days to weeks to months to get a full suite of radiochemical diagnostics. So one of our key focal points is trying to develop faster methods to get that information. And one of the things we're looking at is a technique called RIMS, resonant ionization mass spectrometry. In that system, you take a solid particle, you zap it with a laser to create a cloud, ideally a cloud of neutral atoms. You come in with a second laser. Second laser is tuned to a resonant frequency for the isotope of interest, so uranium or plutonium would be a first question, and preferentially ionizes only those atoms. And then you just use mass spectrometry, use an extraction grid to make a spectrum of the outcoming ions. So this is a way to go from days to weeks to months to days to weeks certainly, and develop information much quicker on the principal isotopes that are present in your debris field. We do a lot of work on seismic and seismology. We help support the nuclear test monitoring system. So the CTBT, for example, has to be underpinned by a clear understanding that if you cheat, someone will know about it, and seismic is one of the key diagnostics. Those signals can't be stopped or masked, and you can measure them all around the world. So our seismic folks have developed amazing capabilities to do detailed modeling of the Earth and Earth motion, and things like earthquakes. We have a group that, if you're in California, the California Academy of Sciences has a planetarium. Their new show is called Earthquake, and it's about the principal focus is the 1906 San Francisco earthquake. The simulations in that show were done by Livermore scientists. So day job, nuclear explosion monitoring around the world. Afternoon fun job, California Academy of Sciences. It's pretty impressive to see a simulation on a 75-foot planetarium dome. It's really cool. And lots of impact in the science and technology community, and this shows a little bit of the range of applications that we have here. The Journal of Virology through to a number of covers of Science magazine, Nature, most of the major physics journals on a routine basis. We're very proud of the impact we have in the scientific community. So I'm going to close here. Well, maybe one thing. So this little instrument on the right side there, that's the GE Mini or Gemini spectrometer. It's a gamma spectrometer, germanium gamma spectrometer. That instrument's being used now for nuclear detection, but it was designed, developed, and built to fly on the Mercury Messenger the spaceship that went to Mercury to make measurements there. So this team built an amazing, compact, mechanically cooled package, since it had to fly on a spaceship, which then was able to move into our national security community pretty seamlessly. So it's kind of cool. Broad range of missions centered around our nuclear core. Really proud of our innovations and our impact, both in the scientific community but in the real world. I think that's an important feature of why I like to go to work every day. And it's about people. That's what really makes our programs go, and what makes the laboratory great, and what makes it a fun environment to work in. So I hope all of you have a chance to come and visit Livermore. So with that, I'll take any questions you might have.